We are going to continue talking about Thevenin and Norton equivalent circuits, but now we are going to introduce what happens when there is a dependent source present. Excuse me, equivalent circuits. So let's start by analyzing a circuit. Let's say that we have a 20-volt source in series with a 6-ohm resistor, in series with a dependent voltage source, carrying a current of voltage of twice Ix, where Ix is the current flowing through this 6-ohm resistor. And then we have a 10-ohm resistor here and a pair of open circuited terminals on our right-hand side. So what we are going to do first is we are going to determine the Thevenin equivalent voltage. So for those of you who are here Wednesday, what do I do? Yeah, we're trying to find a Thevenin equivalent voltage. The Thevenin equivalent voltage of this circuit is defined to be the voltage drop over the open circuited terminals. So I literally just take this circuit, just redrawing it quickly. You don't have to redraw it if you don't particularly want to. And we're just finding this voltage VTH. How we do that is entirely up to us. So what would your suggestion be here? So I'm going to talk about why I don't think nodal is appropriate here. Okay. Now I understand why you would suggest nodal, because we are trying to find a voltage, and nodal analysis gives us voltages pretty easily. As it's drawn, this circuit has 1, 2, 3, 4, 5 nodes. There are a couple of things that we could do to make some of those nodes really not matter. But let's consider something else briefly here. What's the voltage drop over the 10-ohm resistor? 0 volts. So what that means is that this voltage drop over the 6-ohm resistor is representative of the Thevenin voltage. Okay? The 10-ohm resistor actually doesn't contribute anything in our Thevenin voltage determination circuit because it's not part of a closed current carrying loop. So I would argue that all we're analyzing here is a single loop circuit, which means Kirchhoff's voltage law and maybe Ohm's law would be a better thing than setting up a system of equations. Okay. So if I write a KVL expression around this loop, noting that the current that's flowing through all of these elements is simply Ix, what I get is negative 20 volts plus 6 ohms times Ix minus 2Ix plus an additional 6 ohms times Ix is equal to 0. Or 6 minus 2 plus 6 is 10 Ix is equal to 20 volts. And therefore, Ix is 2 amps and VTH is 2 times 6 is 12 volts. For me, that was a little easier than setting up and solving a system of equations. So I try to look at easy methods to do my analysis first, KCL, KVL, Ohm's law, and things like that. And then if that doesn't pan out, that's when I go towards nodal or mesh analysis. So how do we feel about this analysis? Any questions, comments, or concerns? Okay, so do we feel comfortable that this is indeed the Thevenin voltage for this particular circuit? All right, now we're going to find the Norton current. So I'm going to take my original circuit. While you guys redraw this, I'm going to ask, how do we measure or calculate our Norton current? I short circuit the terminals, and then what do? Measure the current flowing through that short circuit, okay? Or calculate the current flowing through that short circuit. So I'm going to short circuit my terminals, and I'm going to define I Norton to be the current flowing down through that short circuit. What circuit analysis technique would you guys like to use for this one? Mesh. That seems, it seems reasonable. A different thing that we could do, where we are going to do mesh, but a different thing that we could do is observe that now our 6 ohm resistor on the right and the 10 ohm resistor are in parallel. If we found the voltage drop over that parallel combination of resistors, which we could get by just doing the exact analysis we did in the other circuit, except put 10 in parallel with 6. If we divided that voltage by 10 ohms, that would also give us our Norton current. That's a couple of steps. Mesh analysis is a couple of steps, so it seems like the same level of difficulty to me. So we'll just do mesh. I just wanted to make you aware of an alternative way of looking at it. All right, so I'm going to call this mesh A, and it has a corresponding mesh current of IA. Let's call this mesh B, which has a corresponding mesh current of IB. We don't have any current sources at all to worry about, so we obviously don't have any current relationships. We do have a dependent source, so we have a controlling variable relationship we need to write. So what's that going to be? Ix is equal to IA minus IB. Exactly correct, Dylan. Thanks. So we have our controlling variable relationship taken care of. As I said a moment ago, we don't have any current sources, so we don't have current relationships to write. So now we just do KVL for mesh A, KVL for mesh B, and solve our system. So KVL around mesh A is going to look like negative 20 volts plus 6 ohms times IA minus 2Ix plus 6 ohms times IA minus IB equal to 0. KVL around mesh B is going to look like 6 ohms times IB minus IA plus 10 ohms times IB is equal to 0. And we can solve this system. excuse me, IA and IB. And it looks like when I did it originally, I just solved it using actually substitution instead of using my calculator. The answer that I get for IB was 120 divided by 136 amps. But if we want to throw it in our calculator and figure out what the quantity A is, we're free to do so. If you want to verify that this is the correct result for IB, by all means, go ahead. So, assuming that my answer for IB is correct, what's I Norton? Yeah, exactly the same as IB. So I'm just going to write this is equal to I Norton. So now let's talk about determining, if we're okay with this, let's talk about determining the Thevenin equivalent resistance. Okay. I'm going to go to the next page. And we're going to call this kind of a new topic because this is where things get slightly different. All right. Method 1. We simply rely on the relationship that we developed in class on Wednesday that says R Thevenin is V Thevenin divided by I Norton. Well, we found V Thevenin, we found I Norton. So we simply take that ratio, okay? So that's 12 volts divided by 120 over 36 amps. And I get 18/5 of an ohm, which is the same as, actually, sorry, I typed in 36, not 136. That's why that seemed aggressively small to me. Let me fix that. There we go, 68 over 5 ohms. My apologies for the mistake. Or 13.6 ohms. Using this method obviously requires us to determine the Thevenin voltage and the Norton current. Okay. Method number 2 is going to be a new thing, except that it's not really a new thing. It is just using the literal definition of Ohm's law and how it is experimentally determined, which we did experimentally on the second day of class to figure out what the Thevenin voltage is. And this is what's called a test source method. So what we are going to do is we are going to exploit the fact that if I have a linear network and I want to determine its equivalent resistance, what I can do is apply voltage Vs measure quantity V test, which should just be exactly Vs, and measure a current I test. And the ratio of these quantities, V test over I test, is exactly the Thevenin resistance. Alternatively, I could have my linear dead network with its pair of terminals. And instead of applying a voltage source, I could apply a current source. And the ratio of V test, the voltage present over the network's terminals, and I test, the current flowing into the network's terminals, is still V test over I test equal to our Thevenin resistance. So it doesn't particularly matter what type of test source that we use. Could be a voltage source, could be a current source. Either way will allow us to determine the Thevenin equivalent resistance. So what we're going to do is we're going to verify effectively that Ohm's law works the way we think it should by applying the test source method both with a voltage source and a current source to our network, and see that we'll get the exact same results as we did taking V Thevenin over I Norton. So I'm going to take my circuit. The first thing I need to realize is whenever I am applying a test source method, it is a means by which we are determining the Thevenin equivalent resistance directly, which means we have to be dealing with a dead network. I cannot emphasize this enough. So if that 20-volt source is on, we are not going to get the correct answer. How do we turn the 20-volt source off, Eric? Yes, exactly right. So to turn a voltage source off, we short circuit it. So my first step is to turn off all of my independent sources, which in this case is only the 20-volt source. Now we need to make a decision whether we want to use a test voltage source or a test current source. We're actually going to do both, so I guess at this point it's which one do you want to do first? Voltage, okay. So we are going to apply a voltage source across these open circuit terminals. Now, this is interesting, and we've actually covered the reason before it, reason why this is going to work before, but it does not matter what polarity we choose, and it does not matter what voltage we choose. We're going to get the same answer regardless, and it's because of the homogeneity property of linearity that we talked about, where we have a simple linear network, so there's going to be a linear relationship between the voltage applied and the current measured. So it literally does not matter what polarity or what magnitude of voltage we choose. So completely arbitrarily, I'm going to choose positive polarity on top, negative polarity on bottom, with a 1-volt source. Okay. If you wanted to do positive polarity on bottom with a 37-volt source, you will literally get the same result. I have just gotten into the habit of using 1-volt sources and 1-amp sources for this. Okay. All right. So from this, rather obviously, our quantity V test is exactly 1 volt. What we now need to find is our current I test. And then the ratio of V test over I test will tell us what our Thevenin resistance is. So what circuit analysis method do you guys want to use to determine the quantity I test? Sure, okay, nodal, why the hell not? I would have chosen mesh, but somebody said nodal, so let's do nodal. So what node do you want to be the reference node? The bottom one, okay. So here's our reference node. So I'm going to call this node A with an associated nodal voltage VA. This node B with an associated nodal voltage VB. And just for the sake of argument here, this node, node C, with an associated nodal voltage, node C. All right, so we have a dependent source, which means we need to write a controlling variable relationship. So how do I express my current Ix in terms of my nodal voltages? VB over 6 ohms, absolutely correct. Okay, we all good with that? I have 2 voltage sources, so I need to come up with 2 voltage relationships. So let's do the 2Ix voltage source first. How do I express the voltage drop over my dependent source in terms of my nodal voltages? VB minus VA, absolutely right. The nodal voltage at the positive polarity terminal minus the nodal voltage at the negative polarity terminal is equal to the voltage supplied by the source. Absolutely right. What about the voltage relationship for my 1 volt test source? Just VC, absolutely correct. Okay, so I have a supernode. Here. And I have a supernode here. The supernode on the right with the 1 volt source contains ground, so I don't need to write a Kirchhoff's current law equation for that one, because anytime my supernode contains ground, I don't write a KCL equation. But my supernode AB does not contain ground, so I do need to write a KCL equation for that. So I'm going to add these currents together. This guy flowing to the left, this guy flowing down, and this guy flowing to the right. I'm going to add those together and set them equal to 0. So what's the current flowing to the left through the 6 ohm resistor look like in terms of our nodal voltages? VA over 6 ohms, absolutely. What about the current flowing down through the 6 ohm resistor in the middle? VB over 6 ohms. And finally, the current flowing to the right through the 10 ohm resistor. VB minus VC over 10 ohms is equal to 0. Absolutely correct. what I'm going to do here is I'm going to substitute in VC is equal to 1 volt into this third equation. And then I'm going to use this guy, and this guy as my system of 3 equations. So my unknown quantities will be VA, VB, and IX, and then solve that system. So for my first equation, I have no VA, 1/6 VB, -1 IX is equal to 0. In my second equation, I have -1 VA, 1 VB, -2 IX is equal to 0. And in my third equation, I have 1/6 VA, 1/6 plus 1/10 VB. No, actually, hold on. No, that's right. Yeah, sorry. Worried myself that I was including VC terms, but they're not showing up anywhere. So sorry, that was my fault. All right, so 1/6 VA, 1/6 plus 1/10 VB, 0 IX, and my my constant term is 1 volt over 10 ohms. Or I just wrote them down poorly here. That's why I confused myself. My apologies. I get 3/17 of a volt for VA, 9/34 of a volt for VB, and 3/68 of an amp for IX. And just to assuage my fears, I'm going to do this again in my system solver just to make sure I didn't make a mistake. All right, so my first equation, no VA, 1/6 VB, -1 IX is equal to 0. We all on board with that. My second equation, -1 VA, +1 VB, -2 IX. All right, and 0 is my constant. My third equation, 1/6 VA, 1/6 plus 1/10 VB, no IX, +1/10. My constant, 3/17, 9/34, 3/68. Okay, I just confused myself slightly when I was doing it, so I just wanted to double check. Okay, so we solved for VA, VB. We know what VC is from our voltage relationship equation. How do we get I test? Yes, it is exactly the opposite of the current as what's flowing through the 10 ohm resistor, which we defined a couple of minutes ago. So let me go back. There's space to do it here. So I test is simply VC, which is 1 volt, minus VB, which is 9/34 of a volt, divided by 10 ohms. Or 5/68 of an amp. From this, Thevenin resistance, RTH, is 1 volt over 5/68 of an amp, which is 68 over 5 ohms, which exactly matches the result we got earlier using V Thevenin divided by I Norton. Okay. Any questions regarding the application of a test voltage source? Okay, so now what we're going to do is we're going to redo the test source method, but use a current source this time. Taking my same circuit. Again, I need to be dealing with a dead network. So I turn off my 20-volt source. I'm going to apply a current source. How I usually do this is with a 1 amp source if I have regular ohm resistors, a milliamp source if I have kilo ohm resistors, and a micro amp source if I have mega ohm size resistors. And it's just to make the voltages not be like kilovolts and megavolts and things like that. Okay, it does not matter. You could just use a 1 amp source for everything. Okay, so our current I test is obviously 1 amps. And now we need to solve for the quantity V test. How would you all care to do this? Mesh, okay? Again, not what I would choose. I would have done nodal here, but let's do it with mesh because that was the suggestion. You guys are keeping me on my toes today. So I'm going to call this mesh on the left, mesh A, which has an associated current IA. I'm going to call this mesh B with an associated mesh current IB. So my meshes have been identified and labeled. I do have a dependent source. So how do I do my controlling variable equation here? How do I express that current IX flowing down through the 6 ohm resistor in terms of my mesh currents? IA minus IB, absolutely correct. I do have a current source, so I need a current source relationship. How do I express the current flowing through the 1 amp source in terms of our mesh currents? Negative IB. Okay. Since that current source is a perimeter current source, we're not going to have to come up with some sort of super mesh equation. So we can simply apply Kirchhoff's current law around node A, and I believe we're finished. Okay. Or excuse me, around mesh A. So that's going to look like 6 ohms times IA minus twice IX plus 6 ohms times IA minus IB is equal to 0. We have 3 equations and 3 unknowns, so I'm going to solve for IA, IB, and IX. So in my first equation, my coefficient for IA is 1, my coefficient for IB is -1, and my coefficient for IX is -1. Constant term is 0. In my second equation, I have 0 IA, -1 IB, 0 IX is equal to 1 amp. Yes, I am that lazy to put that in as an equation in my calculator. For my third equation, I have 6 IA plus another 6 IA, so that's 6 plus 6, For IB, I have -6. For IX, I have -2. And my constant term is 0. And I shall solve. And I get IA is -2/5 of an amp. IB, -1 amp. And IX is +3/5 of an amp. So now that we know these mesh currents, how do we determine our voltage V test? So I would argue, based on the polarity of the voltage we're looking for, that's going to be the voltage drop over the 10 ohm resistor, positive polarity on the right, plus the voltage drop over the 6 ohm resistor in the middle, positive polarity on top. So I'm assigning those polarities from doing Kirchhoff's voltage law in my head, which tells me that V test should be the voltage drop over the 10 ohm resistor plus the voltage drop over the 6 ohm resistor with those polarities. Is that clear, or do I need to explicitly write out the KVL equation? I'm happy to do that if it's unclear as to what I'm doing here. Exactly right. A positive V test on the other side. Exactly right. Okay, so you all seem to be catching what I'm throwing here. So how do I express the voltage drop over the 10 ohm resistor with the positive polarity on the right?
10 ohms times IB.
It'll be 10 ohms times negative IB because IB is flowing into the negative polarity terminal. So that's 10 ohms times -1 amp. And then the voltage drop over my 6 ohm resistor, positive polarity on top, is going to be 6 ohms times, we could either call it IX or we could call it IA minus IB. Right? Voltage drop over the 6 ohm resistor. So let's just call it IX for simplicity's sake, since we already know what that quantity is. So that's 3/5 of an amp. And 10 times 1 is 10, plus 18 over 5, which is 6 times 3 over 5, is 68/5 of a volt. And from this, our Thevenin equivalent resistance is V test 68/5 of a volt divided by 1 amp gives us 68/5. Okay, so we have applied two different methods. We could arguably call it three different methods to determine the Thevenin equivalent resistance of this network that contains a dependent source. The first method involves using the Thevenin equivalent voltage and the Norton equivalent current and taking the ratio of those two quantities, which gives us, by definition, our Thevenin resistance. Our next method involved looking at a dead network, applying a test voltage source, measuring a test current, and then taking the ratio of V test to I test, which gave us our Thevenin. And then our third method, or method 2B, whatever you want to call it, involved applying a test current source, measuring a test voltage, and then a ratio again of the test voltage to the test current was our Thevenin. So anytime there is a dependent source in the circuit, any of those options is valid. If you have a circuit or network that contains only dependent sources, or you just want to get the Thevenin equivalent resistance directly, you can only use the test source method, right? So what I mean by that, let's see if I have one here. If we had the following circuit, there are no independent sources in this network, which means we can't calculate the Thevenin voltage or the Norton current. Our only method to determine the Thevenin equivalent resistance of this is to use a test source method. So just as a quick thing here, which test source do you think we should apply here? Now, I want to preface this by saying we can use either and we'll get the exact same result. We just proved that. But for this particular circuit, its configuration makes one option a better choice than the other. Voltage, why? Exactly right. So what Nathaniel suggested is that if we were to apply a voltage source here, just simply a 1 volt source because that's how I like to do it, effectively the quantity Ix is no longer an unknown thing. It's 1 volt over 10 ohms. We don't have to do any work for that relationship or anything in particular, which to me makes the circuit a little bit easier to solve because our dependent sources are a little less dependent than they were before we knew that, right? So if this is our current I test, recognizing that Ix is simply 1 volt over 10 ohms, I can see, instead of using mesh or something arguably difficult like that, I test is just the current flowing down through our 10 ohm resistor. So that's Ix plus the current flowing to the right through the 5 ohm resistor, which is 1 volt minus 2Ix over 5 ohms. And I would simply just substitute in my value for Ix. And we've determined I test and therefore our Thevenin equivalent resistance with a minimal amount of effort due to our good choice of test source. Does that make sense? You nodding your head because you agree or because you want me to stop talking? All right. So that's enough out of me for today. So you guys have an in-class assignment. There's also a mini lab, which I forgot to print that out. So I'm going to upload it and then print it and run across the street to Nathan to grab it from the printer while you guys are working on the in-class assignment.